Okay? Now we're going to sort of work the other way. Now it may become necessary for us to figure out if two lines are parallel or not. And there are a couple of different ways that we can do that. And we'll take a look at those today. Okay? Those are the standards we're going to hit. They're there for you. So the whole point today, we're going to try to find and use slopes of lines. That's one way that we're going to tell if two lines are parallel or perpendicular. We're also going to talk about using these angle relationships to help us prove that two lines are parallel. Okay? So, first things first, we want to remember what the converse was, right? From the last chapter. And remember, the converse is you just take a conditional statement and you flip-flop the hypothesis and the conclusion. Right? So, for example, if your conditional statement is if you are a clown, then you are funny, then the converse would just be flipping that around, right? If you are funny, then you are a clown. That's basically what we're going to do with our postulate in the three theorems that we had from section 3.2. All right? So, again, postulate 15, or the corresponding angle postulate from the last section, which said that if two parallel lines are cut by a transversal, then the corresponding angles are congruent. Right? If we were to write the converse of postulate 15, that would sound like what? Pretty close to there. It should actually read something like this: if two lines, or I like what you started out with. If the corresponding angles are congruent, then the two lines that are cut by the transversal have to be parallel. Okay? This is the actual wording of the converse, which is a little wordy. But basically, if the corresponding angles are congruent, then the two lines that are being cut by the transversal to create those angles have to be congruent. Have to be parallel. Lines can't be congruent. Okay? So it's the parallel lines that we are wanting to conclude there. Okay? As a matter of fact, this is another postulate. Postulate 16. I think you'll also find it called corresponding angle converse postulate. We'll find better ways to write it other than postulate 16. Okay? And that's true too. You can almost create a biconditional statement then with these two, right? All right? So what does that look like? So we have to make sure that we understand that there is a difference between these two postulates, postulate 15 and postulate 16, and it's all about what we know and when we know it. Okay? What we know and what it is that we want to go find out. So in the corresponding angles postulate, we already know that the two lines are parallel. Okay? And because the two lines are parallel, then we know that those corresponding angles are going to be congruent. Okay? So we knew the lines were parallel first. Because of that, we knew that the that the corresponding angles have to be congruent. Now it's exactly in reverse, right? Now we're going to know, hopefully, that the corresponding angles are congruent first, right? And once we know that, then we'll know that the lines are parallel. Again, it's all about what we know and when we know it. Okay? It's all about what we know and when we know it. All right? All right. So some ways that we can use this postulate to help us figure out if lines are parallel, right? So here we can find the value of x that would make these two lines parallel. Okay? Well, we just saw that if the corresponding angles are congruent, then the two lines are going to be parallel. Right? So we would need these guys right here to be congruent. Well, if they're going to be congruent, then we know that 3x plus 5 and 65 have to be equal. Right? And so we just set them equal to each other. Go solve. And realize that x would have to be 20 in order for line M and N to be parallel. Okay? So we're still basically using the same information as from 3.2. It's just using the information to talk about something different. Okay? To prove these lines are parallel. Okay? And blah, 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 blah. There we go. Okay? Now, more converses. And all we're going to do is from section 3.2, we're just going to flip all of those theorems around, right? And again, it's all about what you know and when you know it. So the alternate interior angle theorem, which says if two parallel lines are cut by a transversal, then the alternate interior angles are congruent. Well, what we can do now is flip that around and say, okay, fine. If we don't know that the angles or that the lines are parallel, if the angles are congruent, if the alternate interior angles are congruent, then that will tell us the lines are parallel. Okay? So again, from section 3.2, if we know the lines are parallel, then the angles are going to be congruent. Now we're saying that if the angles are congruent, then the lines have to be parallel. Okay? So by the time you get these pictures marked, they're going to look the same. To help identify the difference, you could do something like this. This is what we know first. And then this is what we know second. I don't know. If you want a sort of quick reference and I have to read the theorems. Right? I don't know. Something like that. Just to understand that it's all about what we know and when we know it. Okay? Alternate interior. See, so far we've got corresponding angles would have to be congruent to show the lines are parallel. Alternate interior angles would have to be congruent to show the lines are parallel. Alternate exterior angles would have to be congruent to show the lines are parallel, right? So again, from before, from section 3.2, if we know the lines are parallel, then the angles are congruent, right? So if the lines are parallel first, then the angles are congruent second. Okay? To now, if the angles are congruent first, then the lines are parallel second. I know I keep saying this, but it's all about what you know and when you know it, as far as which theorem or postulate you're going to end up using, which will only matter in a proof, right? Or if you have to justify what it is that you're doing. Okay? So corresponding angles have to be congruent. Alternate interior, alternate exterior have to be congruent. Consecutive interior angles have to be congruent. Ooh, stop. Not congruent, right? Supplementary. 3 sets are congruent. The 4th set supplementary, and the 4th set that are supplementary, the consecutive interior angles, right? But it works the same way as the others. Okay? So from before, from section 3.2, if the consecutive interior angles are supplementary, oh, sorry, that's not right. If from 3.2, it was if the lines were parallel, then the consecutive interior angles would be supplementary. Now it's if the consecutive interior angles are supplementary, then the lines are parallel. Okay? So that kind of gets us through all of the theorems and postulates. Now we want to use them. Okay? All right. So your snake pattern's there from your notes. How can you tell what are the sides of the pattern? So this is a snake pattern here, the diamondback snake. How can you tell whether the sides of the pattern are parallel in the photo? Okay. Why do we care? Might be another decent question to ask. I don't know. Anybody that are huge snake fans or biology fans, maybe there's some particular reason why. But anyway, if we wanted to know that the sides of these patterns, if they're parallel or not, okay, well, we can make lines out of the sides, out of those sides, and then draw a transversal through it. Okay, and if we know that the angles that are formed by those two lines in the transversal are, in this particular case, those particular angles, which are, what type of angles? What are these? Interior, what kind of interior? Yeah, alternate interior angles. Since they're congruent, then we'll know that these guys, that the sides of these patterns are parallel, right? Right, so since the alternate interior angles are congruent, the sides of the pattern are parallel. Okay? Or your parallel pattern, your parallel symbol, right? That means parallel. All right? All right. So, some more relevant to what we're going to do examples here. Is there enough information to conclude that line M and line N are parallel? Think about that for a second. Okay, so are these two lines parallel? Yes. And Ben started talking about corresponding angles, and so we can do that here too. The corresponding angle to the 75-degree angle is here, and that's going to be 75 also because they're a linear pair. And so we have enough information to make those two lines parallel. Okay. What about in the second one? Are those two lines going to be parallel? Can you prove that lines A and B are parallel? If the measure of angle 1 plus the measure of angle 2 equals 180 degrees. Just knowing that the measure of angle 1 plus the measure of angle 2 equals 180, is that enough? What kind of angles are angle 1 and 2? Mackenzie? Yeah, they're alternate interior. Yeah. And alternate interior angles have to be what in order for those two lines to be parallel? Congruent. Are they? Is that what that says? Okay. It just says they add to 180. Okay. So is that enough information by itself? No. Supplementary angles do not have to be congruent. They can be. Supplementary angles can be congruent if they're both 90 degrees, right? If they're both right angles. But those angles have to be congruent, right? Okay. All right. All right, and then our proof, and this one was kind of, you had some information left out of this, so we want to prove that line G and line H are parallel, and what was supposed to have been given to you was that angle 4 was congruent to angle 5, which would make this a fairly short proof. But what we're trying to prove here in this particular example is we're trying to prove the alternate interior angles converse. And so we don't want to use that to prove the lines parallel. Okay? The alternate interior angles converse is what says that if the two alternate interior angles are congruent, then the lines are parallel. We're trying to prove that theorem. So we don't want to use that theorem in here. So the proof isn't going to be quite as short as it could be once we have this theorem proven, right? In a two-column proof, you always start with given. Okay? So we're given that angle 4 and angle 5 are congruent. Next step. Next statement. Where do you want to go next?
I have a question. Why do we have to prove it if we already know that they're congruent?
All right. So next step, next statement. What can we say now? Not much we can go with from the given. Got an idea? Kinsey? They are alternate interior angles. That's true. But we're not going to use the fact that they're congruent to show the lines are parallel. That's the theorem we're trying to prove, right? So let's go somewhere else. If you look in the picture, angle 1 and angle 4 are what kind of angles? They are acute, but what kind of relationship do they have? Because they are what kind of relationship do they have? Angle 1 and angle 4 are vertical angles, right? Okay? And that's by the definition of vertical angles. Okay? And now because 1 and 4 are vertical angles, then we know that 1 and 4 are congruent. That's by the vertical angles congruence theorem. I'll abbreviate it as vertical angles congruent. Okay, now we got angle 4 congruent to angle 5, and then angle 1 congruent to angle 4. So now we can say that angle 1 is congruent to angle 5 because of transitive or substitution. The way this is set up is it should be transitive. Question, Jordan?
What is number 3 say?
The vertical angles congruence theorem. Vertical angles congruence theorem. It's a bunch of abbreviations. That's supposed to be an angle symbol, and then the congruent symbol after it. Okay, now that angle 1 and angle 5 are congruent, we can say the two lines are parallel. Yeah, you can't see that. We can say the two lines are parallel. G is parallel to H. And the reason is we're using that corresponding angles converse postulate, which you're not going to be able to see either. So the corresponding angles, converse postulate. Okay? Is that last step there? Okay, so we just we've proven the alternate interior angles converse theorem, so we're okay using it from here on out. Okay, all right. Any questions so far about these converses? Okay. Oop. Then we have the transitive property of congruence, which we just used in our proof, right? There's also the transitive property of parallel lines. Okay? The transitive property of parallel lines, which says that basically if two lines are parallel to the same line, then they're going to be parallel to each other. Okay? So here, if P and Q are parallel, and we know that Q and R are parallel, then P and R are going to be parallel. Okay. It looks just like transitive, sounds just like transitive, and so we call it transitive. It's just a different transitive for parallel lines instead of congruence, but it doesn't matter. We just call it transitive and we're good. Okay? And so we can use that as well. The flag of US has 13 alternating red and white stripes. Each stripe is parallel with the stripe immediately below it. Explain why the top stripe is parallel to the bottom stripe. Well, we just talked about it. Okay? Why is S1 parallel to S13? Okay? Well, because we can continue to use the transitive property all the way down the line. Right? S1 is parallel to S2. S2 is parallel to S3. So on and so forth, all the way down to S13. So because of this transitive property, we just assume, okay, that S1 is parallel to S13. Same thing for if you ever lay in a wood floor, right? If you ever put a wood floor in your house, it's the same thing. As long as you make sure that the first plank is parallel to the second plank, which is parallel to the third plank, and you know that the first plank and the 50th plank are going to be parallel. Right? It's the same deal. All right? All right. The second way we were going to try to talk about lines being parallel. Okay? We're going to go back to algebra class for a second. Which may or may not make you guys happy. Okay? But this is Algebra 1 in about 15 seconds. What's that? Okay? Find and use slopes. Okay? And you've seen this before. You've talked about parallel and perpendicular lines in Algebra 1 class with the slopes. We're going to do it again here. Okay? Quick definition, the slope of a non-vertical line is the ratio of vertical change to the horizontal change. Rise and run. The change in y over the change in x. There's a lot of ways to talk about that. Change in y over the change in x is how I always think about slope. Slope does not tell you the length of a line. Slope does not tell you if two lines are congruent. First and foremost, because lines can't be congruent, since lines extend forever. Slopes only tell us the ratio of the change in y over the change in x, or the steepness of a line, right? Now, how do you find the slope of a line? Well, it only makes sense if we plot that line in the coordinate plane, the xy axes.
Teachers and students, pardon this interruption.
So we plot a line in the coordinate axes, in the coordinate plane, xy axes, and then we can start using their coordinates to help find slope. If you have it in the coordinate plane, you can count rise over run. Okay? Or if we just have a couple of points, we can find the slope of that line by simply subtracting the y's and then putting it over to subtracting the x's. Now, to this point, we haven't really cared about the order of your x's and your y's with the distance formula or the midpoint formula, but with slope, we do. Whichever point you start with for your y, you have to start with your x, so make sure that you're careful about that. Okay, but we're going to find some slopes here and then talk about those lines being parallel or perpendicular or whatnot. Okay? All right. If a line has a negative slope, how would that go? How would that look? Negative slope means your line goes where? What's that? Left to right, up or down?
Down.
Negative means we're going to go down. Whoops. Okay. Negative slope falls from left to right, goes down to the right. Okay? Positive slope goes up to the right. Zero slope. Yes. An undefined slope. Okay? And there are reasons for that, right? In a horizontal line, if you were to write the change in y over the change in x, in a horizontal line, there is no change in y, so that change would be 0. But there is some change in x, so you would have, I don't know, some number down here. That's why the slope is 0. For a vertical line, you do have some change in y, but you do not have a change in x. And so you cannot divide by 0, so we call it an undefined slope. Some quick reminders. There's also this thing, Vux and Hoy. You guys ever talk about that in algebra 1? Vux and Hoy. You ever heard of that?
You say boy or boy?
Vux and Hoy. Right? Vux and Hoy. Vux, V, vertical. So those actually should be flipped around. But anyway, a vertical line has an undefined slope, and the equation is x equals some number. Hoy is a horizontal line, has a 0 slope, and the equation of that line is y equals some number. Something else I've used to remember that too. But anyway. Okay? All right. So find slopes. We're going to find some slopes real quick. We're going to find the slope of line A and find the slope of line D. I'll give you about a 5-second head start. Okay, there you go. There's your head start. Line A. We've got this point here and this point here that are on line A. So we can use those 2 points to help us find the slope. Y2 minus Y1. It doesn't matter which point you make the second point, as long as you make it the second point all the time. So the y's, subtract the y's. We can go 2 minus 4. If I make this 0.2 and this 0.1, then we can go 2 minus 4 over 8 minus 6. Right? 2 minus 4 is negative 2. 8 minus 6 is 2. So slope is negative 1, although slope is always very useful to be left as a fraction. So negative 1 over 1. Okay? Don't have to, but I think it's useful if slope stays as a fraction. Oh. Yeah.
Does it matter which way you write it?
What do you mean, as far as a fraction or not a fraction?
Because I did like 4 minus 2 minus 6 over 8. And I still got
True. So if you made the top point your second point and the bottom one your first point, that's fine. Yeah, as long as you go the same way for your y's and your x's, it doesn't matter. Okay? Now, line D uses this point and this point. So just by the formula, you get 0 minus 4 over 6 minus 6, which is what I was talking about before. Now it's negative 4 over 0. Can't divide by 0, so this is undefined. Okay? Not to mention it's a vertical line, so Vux tells us that a vertical line has an undefined slope. Okay?
Can you just look at it and just say undefined? Or do you have to go through it?
As long as you tell me that a vertical line has an undefined slope, that's fine. Yep. Don't need to see any work there. Okay? Any other questions? Okay. Whoop. Couple of postulates for you, and hopefully, again, like I said, you remember from Algebra 1, but if not, we'll remind you. Slopes. If 2 lines are parallel, what's true about their slopes? Do you remember? Yes, they're the same. Good. 2 non-vertical lines are parallel if and only if, there's the biconditional statement, if and only if they have the same slope. Perpendicular lines have what kind of slopes? Anybody remember that? Are they going to be equal? Well, if parallel lines have equal slopes, are perpendicular lines going to have equal slopes? No. Okay. Oh, real quick, any 2 vertical lines are going to be parallel. And the only reason we add that second little bullet point there is because, again, vertical lines have undefined slopes, and so they can't really have equal slopes if they're undefined. But anyway, vertical lines are going to be parallel. I think that's pretty obvious. Perpendicular lines, their slopes are going to be negative reciprocals. Okay? In other words, if you were to take their two slopes and multiply them together, their product would be negative 1. Okay? But they're going to be negative reciprocals of each other. So either way you want to look at it, and I'll show you both. Okay? And automatically we know that horizontal and vertical lines are perpendicular to each other. Even though one slope is 0 and the other one's undefined. Okay? They're still going to be perpendicular to each other. Okay? All right. Which lines are parallel? Find the slope of each line. Which lines are parallel? We can use the formula if you would like, but we can also shortcut this a little bit and just count rise over run, right? So, the slope of the blue line. Rise. How far do you have to rise from one point to the next? You have to go up. 1, 2, 3, 4. Up is positive. Then you have to run to the right 1. So that's positive as well. 4 over 1. The slope of the red line. Rise. 1, 2, 3, 4. Run 1. Slope of the green line. You have to rise. 1, 2, 3, 4, 5. And then run over 1. Okay? And you see here, since the blue line and the red line have the same slope, then K1 is parallel to K2. Okay, remember the parallel symbol. Just your two, what look like parallel lines. Okay? But obviously K3 is not parallel to either one of those other two guys. All right? Counting rise over run is perfectly fine with me too. If you don't want to have to plug it into the formula. But if you like formulas, feel free to use that. Okay? So there's that. Now, drawing a perpendicular line. So line H passes through the point 3, 0 and 7, 6. Graph the line perpendicular to H that passes through the point 2, 5. And the line's already drawn in here for you. Okay? But if we were to do that, so the line H passes through the point 3, 0, 7, 6. Get to this last example. We should be in good shape, right? So graph the line perpendicular to H that passes through the point 2, 5. Well, if I want line H, or if I want a line perpendicular to line H, then it would be helpful if we had line H's slope, right? So line H has the slope of, use the formula if you'd like. I'm going to count rise over run. You got to rise. 1, 2, 3, 4, 5, 6. So positive 6. And you have to run 1, 2, 3, 4. So proper notation here would say that the slope of H is 3 over 2, which means that the slope of a perpendicular line has to be, well, they have to be opposite reciprocals. So the perpendicular slope would have to be, flip it and switch it, negative 2/3. Okay? The perpendicular slope would have to be negative 2/3. You flip the slope and change the sign. Now, by definition, if you were to multiply those two slopes out, you should get -1. Feel free to check that if you'd like. Okay? Now, I know the line's already drawn, but since the slope has to be, -2/3, and the line needs to go through the point 2, 5, so you start at 2, 5, and then just follow the slope, rise and then run. Since the rise is -2, you can drop down 2 and then run to the right 1, 2, 3, and that gets you your next point. Draw your line to those 2 points, and you've got a perpendicular line. Okay? Make sense? Right? Okay. All right.